So, a couple of announcements before we start the discussion. So, the first thing is yesterday I shared a message in general channel of our team about verifying if you can see the mathematical equation in that Moodle thing. Okay, so you are requested to positively check if you are able to see that equation. Some of you had problem in reading the math equations in the last class test. Okay, so try to sort this problem out as soon as possible, and if the problem still persists, even if by changing the browser or adding some plugin or something, you still cannot see those math equations, then please write to Professor Buddhananda Banerjee. His email ID is given in that message with the screenshot of the problem, like what is it that you see. So during the exam, it will be very difficult and you will waste a lot of time. Last time, some people had this problem. So I would request to take that part seriously if you have a problem and make sure that you are able to see the math question. Okay. That is first thing. The second thing that I want to say is that the class test, second class test, as you know, is scheduled next week. So our slot is B slot. So we will have our exam on Monday, like last class test, okay, during the class hours. So again, you have to log in well in advance for the class test. The pattern is same. You'll have 10 questions, no back navigation, and I think 45 minutes you had last time. Same thing. 45 minutes this time for 10 questions. Okay. So that is what we have. So I will send a schedule after the class. I'll share it in the general channel of our team. Okay. So please. Keep an eye open for that message as well. And the document will contain everything about syllabus and everything like class tests. So please go through both these things very carefully. Make sure that you have no problem. Okay. Okay. So now that these announcements are out of the way, let us continue our discussion. So what we have been doing is we started with this continuous random vector, right? So we had quite a interesting discussion on discrete random vectors, and now we come to this continuous random vectors. Okay. So in continuous random vectors, we already saw uh, in yesterday's class, we already saw like joint PDF. So we started with joint CDF, correct? From joint CDF, we defined joint PDF. Then we define marginal PDFs, right? So that is what we did, marginal PDFs. And then what did we do? We did the what do you say, definition of independence, right? Independence of random variables. So this is what we have done so far in case of continuous random vectors. So this marginal PDF, so everything was done in case of R is equal to 2, but you can very easily generalize to any arbitrary R, right? So that is something that you can do very easily. So double integration will get replaced by triple integration of 4 or 5 or R integral, right? So that is what will happen, and all the definitions will extend very easily. So I hope that you can do. I will not spend time on that. Okay. So this is what we started with, and drawing parallel with the discrete random vector. The next thing that we want to really learn is that if we have independent random variables, then we would like to understand how the sums of independent random variables, or how the quotients of independent random variables really behave. Okay, so we want to find out the distributions. Okay, so that's what we want to do. So like last slide in yesterday's class, let us repeat. Okay, so let x and y be continuous random variables. So let x and y be continuous random variables with joint PDF f of x y. Okay, and we define the new random variable z to be equal to phi of xy. Okay, so this phi of xy is a function basically from R to R. Okay, so this phi of xy basically is a function from R to R. So that's the transformation. And then what did we do? We did following. So for a fixed z, in R, we are interested in this event. Okay, we are interested in the event. So what is the event we are interested in? We are interested in the event set of all z less than or equal to z. And why are we interested in this event? We are interested in this event because for any fixed z, if you are able to find out probability of this particular event, then basically you are characterizing the cumulative distribution function of z. And once you do that, then you basically know the PDF of z just by differentiating it, right? So same logic, same idea that we had used in transformation. We first look for the CDF, right? So that's what we are doing. So let us look for the CDF of this capital Z. Okay, so that's what I'm going to do. But now what I'm going to do in the previous cases when we had CDF of Z, we only had one random variable x, right? And Z was phi of x. So I was trying to represent this event Z less than or equal to Z as x less than or equal to something, right? So that's what I was trying to do. So the same thing I'm trying to do here, but now I have, instead of two random variables, so I have a joint PDF. And because I have a joint PDF, I'll have a area in R2 which will correspond to this particular event, right? Rather than a subset of R, I'll have a subset of R2 which will correspond to this event. So that's all I'm going to do. The idea, if you remember, the idea is exactly the same. Okay. So now I define by AZ subset of R2, define this. Okay, so this AZ is defined like this. Set of all xy, set of all pairs xy, such that phi of xy is less than or equal to z. Okay, so set of all xy such that phi of xy is less than or equal to phi of xy, because you have phi of xy as your transformation, right? So this capital FZZ, which is nothing but probability of this particular event that we are interested in, Z less than or equal to Z, is basically same as saying probability that this random vector XY belong to this particular set AZ. And if that is what we are looking at, what is this probability? This probability is basically a double integral over this Az fxy dx dy. Correct? So basically, your fzz, this fzz, the CDF of random variable z, is basically equal to this double integration, right? So this is how I have expressed CDF of Z in terms of X and Y random variable, right? So that is what I have done. And now what I am interested in basically, is that this particular transformation, phi of XY, I am interested in two transformations. So one transformation is phi of xy is equal to x plus y, and the other transformation is phi of xy is equal to x by y. Okay, x divided by y. So once I understand these two transformations and how I can compute this CDF of z and hence PDF of z by differentiating, I will use these results extensively later on to come up with some interesting sampling distributions and so on and so forth. So that's why these two things are really important for me. So I hope this part is clear. This is something that we had done yesterday. Is there any doubt about this part? Okay. In that case, we can go further and let us talk about this distribution of sums. Okay. Distribution of sum. So what I'm saying is this phi of xy is basically equal to x plus y. That is the transformation that I'm really looking at. So what is the set AZ? So the set AZ is basically the set of all pairs XY such that phi of XY, which is nothing but X plus Y, is less than or equal to Z for a fixed Z in R, right? So what is fixed? So Z is a real number, it is fixed in R. So it is like Z is equal to 3, Z is equal to -2, Z is equal to 1. These are the different values of Z you are going to look at, right? So for example, for one particular value of Z, X plus Y is equal to Z. So geometrically in R2 plane, how will this AZ really look like? So X plus Y is basically a line which looks like this, right? So for positive Z, some Z, so this is the line X plus Y is equal to Z, right? So this is the point Z0 and this is the point 0Z, right? So Z is positive, so this is how it will look like. And this particular region AZ is then basically this shaded region, right? So this entire half plane that you see here. So this is your AZ. This is your AZ. Okay. So for another value of Z, say for example, if your line X plus Y is equal to Z looks like this. Okay. This is another value of Z that you choose. X plus Y equal to Z looks like this. So this is the point and this is the point. So this is the point Z0. This is the point Z0 and this is the point 0 minus Z, right? So 0 Z. So this is what Z is. So Z is negative basically, right? So if you take Z is equal to this, then what is the set AZ going to look like? The set AZ is going to look like this half plane, right? The pink shaded half plane is basically how your X plus Y less than or equal to Z is going to look like. So this is the set AZ for this particular place, right? So for different values of Z, you will have different half planes, basically these planes that you will have. And for those different values of Z's, what you are really going to do, you are going to find out the probability, you are going to find out probability over this AZ, right? So this is the probability that you are interested in calculating, right? So this is the probability that you are interested in calculating, and this probability will calculate, right? So we are interested in computing probability of xy belonging to AZ, right? And this probability, how is it given? It is given by double integral over AZ f of xy dx dy. Okay, so the joint density f of xy dx dy is already given to us, and you have to integrate over this AZ. So you fix the value of Z, and then you know which area, which region in R2 you are really looking at. So that's all we have to do, right? So once you understand this, then there is nothing much. So this particular FZ CDF of Z is basically double integral AZ fxy dx dy, right? So this I will write down as minus infinity to infinity. First I'll integrate with respect to y. So when I am integrating with respect to y, do you all agree that these are the limits that I'll have for integration? F of xy dy dx. Do you agree? So when I am integrating with respect to y, so I am doing it with the red pen now. So when I am integrating with respect to y, then what am I doing? So integrating with respect to y, I am first integrating with respect to this line, right? So this is the line on which I am integrating. So on this line, what are the limits of y? The limits of y are from minus infinity to this particular line. So what is the line? Y value z minus x, right? So from minus infinity to z minus x. That means that you are integrating over this line, red line. And then what you are supposed to do? You are supposed to sweep this line over all the range of x. So the range of x goes from all the way minus infinity to plus infinity, so that you will have all these red lines covered, right? So all these red lines are covered. And when you cover all these red lines, then you have swept the entire region AZ, and that's the integration that you have. I hope you understand this double integration idea, right? So this double integration idea will tell you that this is how you really are going to work with. And now I'll do the simplification in this integral. So I will substitute y is equal to v minus x in the inner integral. Okay. So substitute y is equal to v minus x in the inner integral. So if I do that, then what happens to the limits of y? So what happens to the limits of y? So when y is equal to minus infinity, v is also equal to minus infinity. When y is equal to z minus x, what happens to v? V is equal to z, right? So that happens to the integration, and dy is equal to dv. So if you understand this, then I'll just write down this inner integral in this particular format. So fz z is equal to minus infinity to infinity, and then by changing the limits, I'll have minus infinity to z, and I'll have f of x v minus x dv dx, right? So that is what we'll have, and I'll change this. I'll change the order of integration. So changing order of integration, again, you see, is not a problem here. Okay. And this is what I have as fzz. And the reason why I have this as fzz is that you see this particular pink box I am highlighting. Okay. So this integral you can evaluate, right? So this integral you can evaluate. And after evaluating this integral, or like this pink box, if you see, then this is the integral. And then you have this minus infinity to z for fz, right? So what is the PDF? So PDF of z is obtained as fzz is equal to d by dz of capital fzz, and if I do d by dz, what will I get? Fz. So that fz I can write as x plus y is basically integral minus infinity to infinity f of x v minus x dx for minus infinity less than z less than infinity. You can take any value of okay, sorry, I made a mistake. When you do substitution, this y is actually z minus x. So this z is coming here, z minus x. So this is the PDF of z. This is exactly same thing that you got. So this is that convolution integral. Okay. So in case of discrete random vector, if you remember, you had gotten something similar to this integral, except that there was summation in place of integral. So that was convolution sum. This is called as convolution integral. Okay. So this integral is called as convolution integral, and this integral fx z minus x dx. Okay, so this is how you compute the PDF of x plus y. Okay, this is something that is very interesting. The result that you saw was that if x and y are independent, then you can write down joint as product of marginals, and then what will you have? You will have f of x plus y z is equal to minus infinity to infinity fxx and fy z minus x, right? Dx less than x less than infinity. So if you have independence of x and y, then this is the joint. This is the result that we use. Joint is equal to product of marginals, and fx and fy are marginals of x and y respectively. Then PDF of z, which is nothing but x plus y, is basically given in this particular. One more interesting thing that you can observe from here, like we observed in case of discrete thing, is that if x and y both are non-negative, then obviously their sum will be non-negative, and then you don't need the limit from 0 to infinity. Then what really happens is that you have this f of x plus y z is basically you get integral 0 to z fx x fy z minus x dx 0 less than z less than 1. Okay, so this is what it is. So this or is equal to 0, otherwise for other values of z like negative z you will have 0. right? So this is something that you get. So I hope this part is clear. So I think the form that you might remember, is this particular form. The form that you saw to this particular integral was something that was very similar that you saw for the discrete random variable space, right? So that's what we have. So let us see how we can apply this result. So let x and y be exponential lambda. So x and y be exponential lambda, and they are independent random variables. So what is the density of fx? It is lambda e power minus lambda x is equal to 0 for x greater than 0 otherwise. And similarly, fyy is lambda e power minus lambda y is equal to 0 for y greater than 0 and otherwise, right? So that is what you have. And what do you want to do? Find the density of x plus 1, right? So that is what basically we want to do. They are independent. So this is the form, right? So they are independent, they are non-negative. So this is the form that you just see here. That is the form that we will use, right? So what will we do? So we'll just write down the formula. F of x plus y z is basically integral 0 to z fxx and fyz minus x dx, right? For z greater than 0. So that is what we have, and is equal to 0 otherwise. So now basically we have to evaluate this integral, right? So for z greater than 0, what will you do? So f of x plus y z is basically integral 0 to z fxx f y z minus x dx, and then you have to substitute, right? So 0 to z. So what is fxx? Fxx for x greater than 0, you see this particular formula. So you have lambda e power minus lambda x. And what is fyy? Lambda e power minus lambda, but you have to evaluate at z minus x. So this is z minus x, and that is what you have. So if this is what you have, how will you simplify this? So when you simplify this, you have lambda, then e power minus lambda x plus e power lambda x will be 1, and e power minus lambda z will come out. E power minus lambda z will come out, and you will have this, correct? So f of x plus y z is basically, sorry, you will have lambda square, right? So you have lambda square e power minus lambda z into z for z greater than 0, right? This is what we have. So if I write it down properly, if I write this down properly, I'll have this PDF of this lambda square z. So lambda square into z e power minus lambda z for z greater than 0 is equal to 0 otherwise. So this is the density. This is the density of x plus y. Can you recognize this density? Is this density something that we have already seen? Have you seen this density before?
The gamma density for
Yes, correct. This is a gamma density, and what are the parameters? So x plus y follows gamma density, and the parameters of this gamma density are 2 lambda,
2.
correct? So lambda to the alpha divided by gamma alpha z to the power alpha minus 1 e to the power minus lambda z, right? That's the density. You substitute alpha is equal to 2, then you get z to the power 2 minus 1, so you have z, and this is what, right? Is that fine? So what did we get? We got that if you have two independent exponential random variables with the same parameter lambda, okay, so you have IID exponential random variables, then some of those IID exponential random variables turns out to be gamma density, right? And you can generalize this result, and you can generalize this result, and you can write this down. X1, X2 up to Xn exp lambda are independent and identically distributed. Excuse me. They are independent and identically distributed. Then excuse me, sum of x1, x2, xn is basically gamma and lambda. Another example, let us see. So let's say excuse me. So x and y are uniform 0, 1 IID, okay? So we are interested in what is f of xy. We have to compute this. And what is f of xy? So first tell me what will be the x plus y range. So you observe that x and y both are non-negative random variables. So the formula, excuse me. So the formula that we will look at is fxx fyz minus x dx, right? So that is the formula that we will look at. And when x and y are uniform random variables, fxx is equal to 1 for this, is equal to 0 otherwise. And similarly, fyy is also equal to 1 for 0 less equal y less equal 1 and is equal to 0 otherwise, right? So in the integral, you are taking the product, the integrand in the x plus y integrand. So this integrand here is basically fx x into fyz minus x, right? So fxx into fyz minus x. So fx is constant 1 and fy is also constant 1. So this product takes only two values, 0 or 1, right? So this takes only two values. Zero or 1. So we have to find out where it takes values 0 and where it takes values 1, right? So if x is between 0 and 1 and z minus x is between 0 and 1, then the product will take value 1, otherwise the product will take value 0, right? So that's what we observe. So fxx into fyz minus x takes value 1, when the arguments are between the range 0 to 1, right? So the argument is 0 less than or equal to x less than 1. And the other argument is z minus x. So this z minus x is less than or equal to 1, right? So that is what you have. So now I'll have the cases based on the value of z. So z obviously will be greater than equal to 0 because x and y are greater than equal to 0. So z can take any real value, but the meaningful values of z are only possibly positive values. Negative values, the PDF will be equal to 0. So this is when z is greater than equal to 0 and is equal to 0 otherwise, right? That is how for the non-negative values, right? So I am starting with z greater than equal to 0. So z greater than equal to 0, I'll divide the range of z into two parts, 0 to 1, 1 to 2 and greater than 2, okay? So if z is between 0 to 1, then integrand has value 1 on the set 0 less than or equal to x less than or equal to z. Correct? So f of x plus y z is basically equal to z on 0 less than or equal to z less than or equal to. So if integrand is taking value 1, then I'm integrating 1 between 0 to z, right? I'm integrating 1 between 0 to z, so I'll have value z. right? And then what happens in the next part of the range? So if I take, so if you want, I can write this down. Integral 0 to z 1 dz is equal to z for 0 less than equal to z less than equal to 1, right? This is what will happen. And if I take z to be equal to, if 1 less than z less than or equal to 2, if I take that, then the integrand has value 1 on the set z minus 1. So z minus 1 less than or equal to x less than or equal to 1. Is that okay? So f of x plus y z is basically now between z minus 1 to 1. Correct? Sorry, this is so this will be equal to 2 minus z, right? This will be equal to 2 minus z for 1 less than z less than or equal to 2. And for z greater than 2, what happens? For z greater than or equal to 2, so if you want, you can take strictly greater than 2, then f of x plus y z is actually equal to 0, right? Because integrand will take 0, 1. So the support of this x plus y is only between 0 to 2. If you have two random variables between 0 to 1, then their addition will have support between 0 to 2. And that's what basically I have done, right? So what is the PDF then? Then the PDF is basically f of x plus y z is equal to 0 for z less than 0 is equal to z for 0 less than equal to z less than equal to 1. 2 minus z for 1 less than z less than or equal to 2 is equal to 0 for z greater than or equal to 8. So this is how the PDF looks like. And if you want to draw the graph of this PDF, then the graph of this PDF is really nice. So it comes all the way as 0. Then you go here, then you come back 2 minus z, and then again it is 0, right? So the values here are 0, 1, 2. So this is how this particular sum x plus y really like. Okay, so this is the addition. Okay. Is that okay? So let's move to another example. So this is only how well you can do and how quickly you can do these integral businesses, right? So if you do integral well, if you remember your integral calculus from your advanced calculus course well, then these things are not really very difficult. Okay. The other thing, let us take another example. So let x follows gamma alpha 1 lambda, and let y follows gamma alpha 2 lambda. Okay. Be independent random variables. Suppose you have these as well independent random variables. Then we want to show what is the density of x plus y. So the density of x plus y is this. Okay, and how do you prove that? Again, so first write down densities of x and y. So this is lambda to the alpha 1 gamma alpha 1 into x to the power alpha 1 minus 1 e to the power minus lambda x. For x greater than 0, this is equal to 0 otherwise, right? So this is the density of fx. So similarly for y, lambda to the power alpha 2 by gamma alpha 2 x to the power alpha 2 minus 1 e to the power minus lambda x for y greater than 0. For y greater than 0 is equal to 0 otherwise, right? So that is what we have. And note that x and y are non-negative. Therefore, what is the density of f of x plus y z? So f of x plus y z will be equal to integral 0 to z fxx fy z minus x dx for z greater than or equal to 0 is equal to 0 otherwise, right? That is how the density of x plus y will look like. So for z greater than 0, let us check. So f of x plus y into z. Okay, so this you have fx and fy z minus x. So these are the things that are going to multiply. So if you will allow me, I'll just write down this. This calculation is not very difficult. Integral 0 to z, and then I have e power minus lambda e power minus lambda x is sitting here because of this, and then what do I have? E power minus z minus x. So I think if you will allow me, I can just write this down as e power minus lambda z. Is that okay? And then I'll have x to the power alpha 1 minus 1, and I'll have z minus x to the power alpha 2 minus 1. Okay. And this is something that I want to simplify, right? So this is something that I want to simplify now. So this simplification, it may not be very easy, or you can do it, that's fine. But typically this is not an easy thing to do. Okay. So you can show though that this is actually the density of gamma alpha 1 plus alpha 2 lambda. Okay. So this integral you have to work out. There is some trick that you have to use to this integral. So rather than using any trick on this integral, we actually do something which we had done previously. Use the moment generating function, right? So couple of examples we saw. This convolution integral evaluation was easy, right? Couple of things we saw. Convolution integral evaluation was easy. So these these exponential densities or uniform densities through geometry and some things, it was easy. But every time it may not be easy to evaluate these convolution integrals, and in order to avoid that, what we will do is we'll do this MGF trick. Okay, what we will do is this moment generating function. So so let us see what we can do. So if x and y are continuous random variables, with joint PDF f of x1, then expectation, I'm going to do expectation of phi x1. Okay, so rather than phi, let us use the same notation that we have used, h of xy. Expectation of h of xy, how will I define? It will be basically double integral of hxy fxy dx dy. If this exists, then we will have this thing, right? So this is how we define expectation. So if this is how we define expectation, let us suppose that you can write down this h of xy into two parts, phi 1x into phi 2y, right? So you can decompose this, and x and y are independent, right? So if that happens, then what will happen? Then you can write down expectation of h of xy. Expectation of h of xy, you can write it down as double integral over phi 1x, phi 2y, fxy, xy, dx dy, right? So this will be phi 1x, phi 2y, fxx, fyy, dx dy. This will happen because of independence, right? So joint is written as product of marginals. This will happen because of independence of x and y. And once you know that, then what can you write? You can write down phi 1x fxx dx into phi 2y fyy dy, right? and this is nothing but expectation of phi 1x into expectation of phi 2y, right? So you can write this down, and then if this phi 1x and phi 2x is moment generating functions, then we can do the moment generating function, right? So 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 let x and y be independent random variables. Then what do we do? Moment generating function of x plus y is what we are interested in. X plus y. We are interested in finding out moment generating function of x plus y is basically mx plus y t is basically expectation of e to the power t x plus y. So what is this? This you can write down as expectation of e to the power tx into e to the power ty. So here h of xy is e to the power tx plus y. You can write it down as phi 1x into phi 2y. Because of independence, you will be able to write this down as e power tx into expectation of e power ty, which is nothing but mxt into myt. Correct? So this is the result that we had proved for discrete random variables also. Same results we can prove for continuous random variable. And if we can do that, then what we have to do is just look at the moment generating functions and see what is really happening, right? So if you want to do that, then we can do that with the gamma case also, right? So let xi follow gamma alpha I lambda for I is equal to 1 to R independent, right? If that is the case, then what is, can you quickly tell me what is mxit? Can you tell me what is mxit? Quickly. Anybody? Can you tell what?
Lambda upon lambda minus t raised to the alpha I.
Lambda divided by lambda minus t to the power alpha, right? That is what we have. And then what will be the mx1 plus x2t? Then it will be the product of mx1t into mx2t. And what will that be? Lambda divided by lambda minus t to the power alpha 1, lambda divided by lambda minus t to the power alpha 2, which is lambda by lambda minus t to the power alpha 1 plus alpha 2, which will imply that x1 plus x2 actually follow gamma density with the parameter alpha 1 plus alpha 2 and lambda 2, right? So this is very easy, moment generating function, right? So again, you have to remember moment generating functions, you have to remember how their forms look like, right? So we'll use the same moment generating function trick in case of normal random variables also. So let x and y be independent random variables with x following normal mu1 sigma 1 square and y following normal mu2 sigma 2 square, right? That is what we have. Then what is the PDF of x plus y? What is the PDF of x plus y? That's the question. So let us write down mx plus yt. So we know that mx plus yt is mxt into myt, right? Because of independence. So what is moment generating function of x?
E to the power mu 2 plus half sigma square t.
E to the power
Mu 1 t plus half sigma 1 square t square.
t square. And similarly here you will have e to the power mu 2 t plus half sigma 2 square t square, right? So now you combine the terms very nicely. They combine mu 1 plus mu 2 t plus half sigma 1 square plus sigma 2 square t, right? So this is what you get. And what does that mean? You can say that x plus y also follows normal density with mu1 plus mu2 as its first parameter, which is mean, and sigma1 square plus sigma2 square is second parameter, which is relative. So x plus y followed this, right? So this is something that is really very interesting. This is very, very interesting results. Moment generating functions actually help us do this thing. So we can generalize this result. So what is the generalization of this result? So you can do the generalization. So let x1, x2, xn, okay, are independent random variables. Okay, they are independent random variables. Then m of x1 plus x2 plus xn t is actually equal to mx1t into mx2t into mxnt, right? This is because of independence. If x1 up to xn are IID, independent and identically distributed random variables, then you can see that x1 plus x2 plus xn t, basically all these mx1 is same as mx2 is same as mxn because they are identically distributed. So you'll have mx1 t to the power n, right? So this is what we have. And you can very easily see these results getting generalized. So if you have xi instead of I is equal to 1 to, if I have I is equal to 1 to n, then you will basically have the exponent. Here I had alpha 1 plus alpha 2. That exponent will be equal to summation alpha I, and then that is the parameter that will sit here, right? Whatever is the exponent that sits here, whatever is the parameter lambda that sits inside lambda. So lambda is not changed. And now you see why in gamma addition I need that lambda not to change, because if lambda changes, then I cannot write it in this very beautiful form, right? So that's the problem. So it will not be gamma. So that's why I need lambda fixed. So that's why when I had exponential densities, I was adding exponential densities. Exponential densities alpha is equal to 1, right? So exponential is gamma 1 lambda, right? So you see, I had gamma 1 lambda. I added n independent gamma 1 lambda. What did I get? I got gamma n lambda. So that's what sum of n independent exponential densities is gamma density. That's how you get this particular result. Is this clear? Are you following this particular thing? Same thing can apply to this normal random variable. So you will have this x plus y. So you'll have x1 plus x2 plus xn, normal mu1 plus mu2 plus mu1, sigma 1 square plus sigma 2 square plus sigma n square. And if all the xi's are IID, then you will have n mu and n sigma square, right? So that's what you do. So I hope these things are clear, right? Any
Yes,
doubt
sir.
about this? Okay, so this is something that we have. So I'll just quickly summarize these things that I had told. So this addition is really very important. So the first thing that we saw was xi are exponential lambda IID. Okay, for I is equal to 1 to up to n. Then summation xi I from 1 to n. It follows gamma density. It follows gamma density, and what are the parameters? Parameters are n lambda, right? So this is the first observation. This is something that we have seen. Then the second thing that we saw is that suppose xi are gamma with alpha and lambda as its parameters, if they are independent. Okay, if they are independent, for I is equal to 1 to up to n. I is equal to 1 to up to n. Then what is summation xi I from 1 to n? It will again follow gamma density. It will again follow gamma density. And what is the parameter? This first parameter is summation alpha I, and second parameter is lambda, right? And what is the third thing? So the third thing that we saw is that xi follow normal density with mu I and sigma I square, right, are independent. Suppose xi are this, they are independent random variables for I is equal to 1 to up to n. right? If that is the case, then summation xi I from 1 to n, what does it follow? It will follow normal density with summation mu I from 1 to n, and summation sigma I square I from 1. Is that okay? Excellent. So one thing that I wanted to talk about here at this particular point is, giving more focus on this number 3 point. Okay. So what is this number 3 point? Xi are normal, mu I, sigma I square. Okay. So let us explore this further. So let x1, x2, xn are IID, normal, mu, sigma square. Okay. So they are independent, identically distributed mu, sigma square. Then you all know that x1 plus x2 plus xn will follow normal with n mu and n sigma square. Is that right? Is that right? And can you tell me what will be the distribution of x bar then? Can you tell me what will be the distribution of x bar?
The mu and sigma
Same.
square by n.
Mu and, yeah, you told
The
me
normal.
yeah, it will be normal. Okay. X bar will follow normal density mu and sigma square by n. There are various ways in which you can prove this result. So you can do the transformation on normal, and you can do, or you can use MGF and you can prove. But the important thing is that if x1, x2, xn are independent, identically distributed normal random variables, then x bar is also normal random. This is something that is really, really very important. Okay, this is something that is really, really very important. What we had seen earlier, is that x1, x2 up to xn are independent with mean mu and variance sigma square. Then we had seen that mean of x bar is also mu and variance of x bar is sigma square by n. But we had not said anything about the distribution of x bar. You have to be careful about this. We had not said anything about distribution of x bar. So same logic that we had proved here, you can see that mean of x bar is mu and variance of x bar is sigma square by n. But if you know these two parameters, then the normal density is unique. But this normality of x bar is not proven. Okay, you have just proven that mean of x bar is mu, which is fine. So this one-to-one correspondence you can have. Variance of x bar is sigma square by n. This is also fine. But how can you say with guarantee that x bar will follow normal if x1, x2, xn are normal? Right? That is something that is really very important, and that holds true only for normal density. In general, we just speak of mean of x bar and variance of x bar. In general, we just speak of mean of x bar and variance of x bar, but we do not speak of distribution of x bar. But if x1, x2, xn are normal mu sigma square, then x bar also is normal distribution with parameters mu and sigma square by n. Do you understand the difference? Do you understand the difference? So this is something that is really very critical. If you understand this, then you will understand something which is called as central limit theorem. So we are going to see something which is called as central limit theorem, which will say that even if x bar in general may not have normal density, you can approximate it by a normal density very nicely. That's what we will see using something which is called as central limit theorem. We'll see that probably next week also. But do you understand the difference? So if you have x1, x2, xn, IID normal mu sigma square, then x bar will be normal density with mu sigma square by n. If you do not have normality, but you only have this condition that x1, x2, xn are independent, they are independent with mean mu and variance sigma square, if that is what you have, Then mean of x bar is mu and variance of x bar is sigma square by n. That is the most general result that we have proved. So this is the most general result. In particular, their IID with normal mu sigma square, then x bar also follows mu sigma square. Okay. So how do you prove that result? So let x1, x2 up to xn for our IID normal mu sigma square. Okay. Then prove that x bar also follows normal density with mean mu and variance sigma square by n. Okay, how do we prove this? How do we prove this? So we start with this moment generating function, which is nothing but mx bar t, right? So what is this? This by definition is expectation of t into x1 plus x2 plus xn divided by n. Is that right? Do you all agree? Then what will you have? So basically what I am trying to do is I am trying to do m of ax plus bt. So if that is the case, then what do you have? Expectation of e power t ax plus b, right? So you have expectation of e to the power b into e to the power t ax. So this is nothing but e to the power b, right, into expectation of e to the power atx, right? So what is this? This is e to the power b and moment generating function of x evaluated at at, right? So this is what you have. So here b is equal to 0 for us, so that is gone. And what is x? So basically x is x1 plus x2 plus xn, right? And a is equal to 1 by n, b is equal to 0 for us. If that is the case, then what do you get? What do you get? You tell me. You have m x1 plus x2 plus xn at which point? T by n. Do you all agree? This is what you have. And this is nothing but mx1 at the place t by n, so on and so forth, mxn at the place t by n, right? But you are given x1, x2, xn are IID, so this is basically mx1 t to the power n to the power n, right? And what is the moment generating function of x1? What is the moment generating function of x1?
e to the power mu t plus sigma
E
square.
power mu t plus sigma square t square by 2. So now you have to evaluate this at t by n. So you are evaluating it at t by n. So you'll have t by n here and you'll have t square by 2n square, right? And this whole thing you will raise to n. So what do you get? So you get e to the power mu t again plus sigma square t square by 2n. That is what you get. So this first parameter is coefficient of t and sigma square n actually is the parameter of coefficient of t square by 2, right? So from here you can show that x bar, so this is the form of normal thing, normal mu sigma square by n. Is that okay? So again, you have to be very sure how you are finding this out, right? So the trick is, if you see e to the power mean into t plus variance into t square by 2, right? This is the form of normal. This is the form of normal MGF, correct? The form of normal MGF is this. What is the MGF we had? The MGF we had was e to the power this plus sigma square t square by 2n, right? That's what we had. So this you can write down as e power mu t plus sigma square by n into t square by 2, right? So this is your mu and this sigma square n is your variance, and you have this form, so it has to be a normal random variable. So it's a normal random variable with two parameters, mu and n, right? So that means that x bar follows normal with mu and sigma square by n. Is this calculation clear?
Yes, sir.
Is this so? Is this clear to everybody what we have done? So again, this is very easy, but it is easy provided that you have like these formulae for MGF, PDF, CDF, everything at the tip of your tongue, right? So if you have that, then you can do these calculations very quickly, very easily, and this is what I have done. Is that fine? Any doubt about what we have done so far today?
Sir,
Oh, yes.
so
Yes,
that
Rich.
that convolution integral that we got, that we said that we could not evaluate and we will go with the variance method,
Hmm. Hmm.
that somehow seemed to be using that beta identity that relates beta to gamma.
Exactly,
Is that
exactly. That's right. So if you know how to relate beta with gamma, then you can do it very easily. But because this is exactly beta, so instead of 1 minus x, you have z minus x, but of course the limit is also up to z. So if you know how to relate this with gamma from beta, you can very easily write it down. That's absolutely right. That's what you have to do. But I did not want to go into that beta gamma relationship by change of variable and doing all those things. So that's why I did not do it, but you can do it. That's why I left it there. That beta gamma identity is exactly what we have. And because we have EC guys here, and I don't know if GG guys learn this systems and signals course, but are EC guys learning this signals and systems course in this particular semester, or in
so
future
we have it in next.
you have it in next semester? Excellent. So if you have this course in next semester, signals and system, then something that you will be doing in signals and system extensively is being already done in this particular course. Okay. So what happens is you will realize in signals and system course, you will realize that you learn something which is called as transfer function, and you will realize that you will have to evaluate convolution integrals extensively. Okay, so if you have to evaluate this convolution integrals extensively, then convolution integral is basically the convolution integral that I told today. Okay, so this is the convolution integral that I have told you today already. So this convolution integral evaluation in general is really a very difficult task. So this particular integral that you see here, like even if in case of independence, this convolution integral evaluation is a very difficult task. And this difficult task of evaluating convolution integral we saw is slightly easier when you go to this moment generating function approach, right? If you go to this moment generating function approach, then it is slightly easier. And what is the definition of moment generating function? The definition of moment generating function is expectation of e power tx. Okay, so this is the moment generating function definition, expectation of e power tx. And what you will see in your signals and system course in next semester is basically how do you evaluate these convolution integrals easily. So you will see that evaluation of convolution integrals can be done very easily by transforming into the S domain. So they will say you go to Laplace transform, you go to Fourier transform, and if you take those transforms, then evaluation of convolution integrals becomes really very easy. Convolution is very easily handled in Laplace or Fourier transform. It's just a product. Okay, so here you see there was convolution integral. That convolution integral just turned into product, right? So in this moment generating function, you just took product here, right? So here, where was that result? So the result was here, right? So here you just take product, right? So this side was relating to convolution. So x1 plus x2, you have to do convolution. So that convolution you can avoid by taking moment generating function. And how do you avoid? You just take product here, right? So this is exactly what happens in Fourier transform. Okay, so this is what you are doing. Convolution you are avoiding by taking product. In Fourier transform, you just take product of the Fourier transform. So you will see that this moment generating function, the way we define it, expectation of e to the power tx. Okay, the way we define it, this e power tx, and this expectation is basically integral e power tx fx dx, right? So this is what you have. So this t, when you take it to be minus j omega and so on and so forth, where j is square root of unity, that complex number, then this becomes Fourier transform, or it becomes Laplace transforms for different choice of t. And you will see that in your signal systems course, you will do this all the time. You will take Fourier transform, and you will take Fourier transform to avoid this convolution integral. So this is something that you can relate very nicely to your Fourier to your signals and systems course. Okay, so this is something that you have to remember. Okay, so this is what you have to learn. These are the ideas in different subjects, but those ideas are not really extremely different ideas. It's just like, you know, translation in probability and statistics. I am saying convolution. I'm saying I want to find out PDF of x plus y, and that convolution is difficult. So I'm doing moment generating function trick. In your signals and system course, you will say that you are interested in evaluating that convolution integral. So that convolution integral evaluation is basically done to Fourier transform, right? So it's just translation. Somebody speaking in Marathi, that gets translated into Hindi, that gets translated into English, that gets translated into Tamil. So same concept in different languages, right? So the concept is same everywhere. The universal concept is same in different languages, in probability theory, in signal system, in differential equations theory. So everywhere you'll use the same concept. The names might be different, but you should be able to relate these ideas. You should be able to see these ideas across different fields. Okay, so this is something that is really very interesting. Unfortunately, you have not yet done this signals and system course, so that's why you will appreciate it in signals and systems course. Okay, so at that time you have to remind yourself that in PropStat we have done this. This is exactly the same thing that we have done in signals and systems, right? So this is something that you have to do. This is what you will have to learn to do, so that you can see, you know, there are only few original interesting ideas. They get translated into different languages in different subjects. Okay, so this is one such brilliant idea. Okay, convolutions, you can do it using transforms. Okay, that's why you learn transforms. So I think GG guys, they will learn transform calculus course possibly. So in the transform calculus course, they are going to do the exact same thing. You see guys, they are going to learn signals and systems. They are going to do the same thing, like same idea in different courses explained in different language. That's all it is. So this is something that is really very beautiful, but that aha moment that you are supposed to get, unfortunately you will not get, because you have not done this. Otherwise you can very easily, when you remember the Fourier transform formula, you can very easily see that how this is related to Fourier transform and Laplace transform and things like that. Unfortunately, I have not done that yet, so you have to remember these things when you learn these transforms. Do those calculations and relate that.
Actually,
Yeah.
so in network theory, we have done convolution, Fourier transform, and Laplace transform, so to say.
So
So
network theory course
we
is
relate.
already done for you. Okay, network theory course is
Yes, so we
already
are
done.
doing it in this
You are doing
semester.
it
So
simultaneously. Excellent. Then in network theory course, if you are doing it simultaneously, then you see I am not doing anything different than what you did in network theory course, right? So this is how you should draw parallels. Okay, this is very important in learning, and this is something that you will get only by discussing with things, right? Otherwise, it is what I am just telling things, formula दे रहा हूँ, तुम लिख रहे हो, evaluate कर रहे हो, but this connection, seeing this connection is really very important. Okay, so you should start learning how to connect these things with each other. Okay, so that's very important. So in network theory, if you have seen this, then you already know the beauty behind this formula and beauty behind the similar things that we are doing. Okay, so that's what I wanted to say about these things. Okay, any other comment that you have, anything that you want to say here, anything that you want to add here before we go further? Anything?
No.
Okay, so if that is what you have to do, then I will do few things that I had said. I have said in passing, and then there are a couple of transformations and distributions I want to introduce that I will introduce today. Okay, so just two three things which are like left hanging I had not done previously. I'll just connect them together and we'll do it. Okay, so before I go into that, let us take a break of couple of minutes. I'll just be back in couple of minutes and then we'll continue. Okay, thank you. Okay, so there are some few things that I had not covered previously, so I just want to kind of like mention those things so that you are not surprised if you see those things in your exam, so to speak. Okay, so I had not introduced two distributions. One is Weibull distribution and one is log normal distribution. So these are the two distributions I just want to mention. And I had told about beta density, but I had not written down things about beta density. So what I'll do is I'll actually write down those things properly today about beta density and this thing, Weibull density and log normal density. Okay, so these are the things that I will actually do today. I'll just write down. There's nothing difficult in all of these things. I'm sure you already have understood that beta thing and all, but I'll just write it down once for the sake of completeness. Okay, so uh, so so some topics I had left maybe as easy exercises. Okay, so I'll just write them down. Okay, for the sake of completion. One thing that we have seen is uh, the exponential density, right? So what we have seen is exponential density, and what we have not seen is Weibull density. Okay, so I'll just write it down. Weibull density. So y is a continuous random variable. Is said to follow Weibull density. With parameters gamma and beta. With parameters gamma and beta, if its PDF is given if its PDF is given as Fy y is equal to gamma by beta. So you have this as gamma by beta, y to the power y gamma minus 1, e to the power minus y gamma divided by beta. Okay, so 0 less than y less than infinity, gamma is strictly greater than 0, beta is also strictly greater than 0. This is the range of parameters. If you have this particular density, PDF, then you have this, right, is equal to 0 otherwise. So if you have this density, then you get this. It's looking difficult, right? It's looking weird, but if you see, if you take gamma is equal to 1, what happens? If you take gamma is equal to 1, what happens?
The exponential y squared.
Then we get exponential density, right?
Yes.
We get exponential density in our notation with parameter 1 by beta, right? Exponential density with parameter 1 by beta. Because what do you get? 1 by beta, y to the power 1 minus 1, 0. So y, that will be 1. So 1 by beta, e to the power minus y by beta, right? So that is exponential density with parameter 1 by beta. So lambda is equal to 1 by beta. That is what you will get. So that is what you have. Okay, so this handwriting, I'm sorry, is really very bad. So this is y to the power gamma, okay, minus y to the power gamma. Sorry about that. So this is what we get. Okay, you put gamma is equal to 1 here, and then you get exponential density. In fact, you can show that you can do this as an exercise. Okay, show that if x follows exponential density with parameter 1 by beta, okay, then y is equal to x to the power 1 by gamma has Weibull density. Okay, this has Weibull density. And how will you work? You know how to work with transformations, right? So you work with transformations, and when you work with transformations, you see this is the result that you will get. So gamma y to the power gamma minus 1. So this term that you see here, oh. So this term that you see here basically is coming out of the derivative of y to the power gamma. Where is y to the power gamma? Y to the power gamma is coming from this x is equal to y to the power gamma, right? So you know what is happening. That derivative term is coming, and then you have this e to the power minus y to the power gamma divided by b. So you will substitute wherever you see x, you will substitute y to the power gamma, right? That's what you will do. So that's how you can derive this result very easily. So that is what you have to do, right? So this is what you will do. Just a minute. So this is what this Weibull density really looks like. So if you had seen this form, suddenly you might get surprised, but it is not. It's just the transformation that we have to look at. Okay, so this transformation is something that I did not do when I was talking of exponential density. Okay, so I am just doing this discussion here. And this Weibull density is really very useful because this Weibull density actually is used to do several modelings in reliability. Okay, so this is something that is important. Live like expected like hazard rates and expected life dependency and like life remaining, expected life remaining, and based on that is reliability things. So that is where this density very naturally comes into the picture. Okay, so there are various places where this density has applications in real life. So I just wanted to note this thing down. So this is Weibull density, and this is the transformation with which you actually get Weibull density. So starting from exponential, you get Weibull. So you see, there are many important links that you have to remember, right? So you started with uniform 0, 1. From uniform 0, 1, you went to that exponential lambda by doing that particular transformation. Then you had from exponential lambda done various transformations and got other densities. So one density that you have done from exponential is this Weibull. Then other thing that you can do from exponential is that you can add n independent exponential densities, and then you'll get gamma and so on and so forth. Right? So that exponential is like base of many other densities. Similarly, I want to talk of beta distribution. Okay, so I want to talk of beta distribution. So this beta family, so a random variable x is said to follow a random variable x is said to follow beta density with parameters alpha and beta. With parameters alpha and beta, if it has the PDF. If it has the PDF, fx is 1 upon b of alpha beta. So we will see what is the b of alpha beta. X to the power alpha minus 1, 1 minus x to the power beta minus 1. Okay, and 0 less than x less than 1 is equal to 0 otherwise. And what is the alpha and beta? So alpha is greater than 0 and beta is greater than 0, right? So these are the things. So you can easily recognize this particular function to be the integrand of the beta integral, right? In the beta integral 0 to 1, this is the integrand, right? So if you have this integrand, you have done beta integral in your advanced calculus course. So from there, what do you know? So where here this beta of b of alpha beta, if you want to call this b of alpha beta, is basically integral 0 to 1 x to the power alpha minus 1 1 minus x to the power beta minus 1 dx. It's like normalizing constant that we are getting here, and this normalizing constant, this is actually given as gamma alpha gamma beta divided by gamma alpha plus beta, right? So that is what we get. So this is the value of this b alpha beta. Okay. And now if that is the case, then moments of beta is very easy. You can very easily see how you can calculate moments of beta. So expected value of x to the power n is basically 1 upon b alpha beta integral 0 to 1. Then you have x to the power n. You have x to the power alpha minus 1, 1 minus x to the power beta minus 1 dx, right? X fx dx, x to the n fx dx. And that's it. Your job is done now, right? So why your job is done? Because this is 1 upon b alpha beta. And what is the evaluation of this integral? The evaluation of this integral is b alpha plus n beta. Correct? That is what we have. And once you have this, then like it's done, right? Job is done. This is what you have. And you have this gamma alpha gamma beta divided by gamma alpha plus beta. So if you have these things, then your job is done. So for n is equal to 1, what happens? For n is equal to 1, what is the expected value of x? Can you tell? What is the expected value of x? For n is equal to 1.
1.
1. How is it 1? Will it be alpha by alpha plus beta? Can you quickly check?
Yes.
Okay. And I will not calculate variance, but you can calculate expectation of x square from here similarly, and expectation of x square minus expectation x whole square. If you do, you can check variance of x will be alpha beta into alpha plus beta whole square into alpha plus beta plus 1. Okay. That is what you get as variance of this beta. You can very easily check. Okay. So that's what you have. So this is what we have as expression of variance. You can quickly check. It's not difficult. Okay, so this is about beta. I had said I'll write it down one day, so I have actually written it down properly. Another distribution that I just wanted to introduce was log normal distribution. So this log normal distribution is related to normal distribution. So what happens in log normal distribution? So if x is a random variable, whose logarithm is normally distributed. Okay. What does that mean? That means that logarithm of x follows normal density with parameters mu and sigma square. Okay. Then x is log norm. Then x has x. Then this random variable x is said to have log normal density. Okay. So log normal density. And the PDF of this, the PDF is given by, what is the PDF? The PDF is given by fx is equal to 1 upon root of 2 pi sigma. So then you have 1 by x, then you have e to the power log x minus mu divided by 2 sigma square, and you have the range 0 less than x less than infinity, and mu and sigma square. Mu is any real number and sigma square is always positive, right? So that is. So this is the PDF. Again, this transformation you can do very quickly, and you can see what is really happening. Okay. So you can see how you can calculate expectation mean of this. Okay, so expectation of x basically will be expectation of e to the power log x, right? And this is basically expectation of e to the power y, where y is equal to log x. Y is equal to log x follows normal with mu sigma square. And you can identify this expectation of e power y as e power yt evaluated at t is equal to 1. So basically this is moment generating function evaluated at t is equal to 1 for the normal random variable y, right? So this you can say is expectation of mu t, t is 1 plus half sigma square t square by 2, t is 1. So this is the mu. So mean of this log normal density is expectation of mu plus sigma square t square by 2. And similarly, you can calculate the variance also. So the variance of x you can show is expect e to the power 2 mu plus sigma square minus e to the power 2 mu plus sigma square. Okay. So you have 2 into mu plus sigma square minus 2 mu plus sigma square. So this is the variance of x. Okay. So this is the variance of x. So this is about log normal density. Okay. So this this density is popular. This density is popular in modeling skew data. Okay, skew data, especially right skewed data. Okay. So this is something that I have not talked about, skewness and kurtosis and all. So I will not go into the details of these things anyway right now. But this is one application. Okay, so this log normal densities actually come into the picture. So this is one of the interesting densities that you have. So this was the beta distribution, and this was the Weibull density. So these are the three densities I had not mentioned. So I have mentioned them today, and this is what I wanted to say about these densities. So anything else about something that I have not covered or I have not said? If you have any doubt about anything that I have not covered.
In assignment 4, there was some approximation that was being talked about in
What
questions.
is that, Priyanshu?
I'll
Can
see
you
it
say it
exactly
again?
what it is.
I cannot hear you properly, Priyanshu. Voice is breaking. Can you say it again?
So in assignment 4 questions, there was something like some approximation to be used in question, like continuous approximation or something like that.
Yeah.
And
So that is something that is something that is related to uh, approximation of a PDF by another PDF, which is related to central limit theorem. So one is central limit theorem, then the other is you can see how you can approximate binomial probabilities by normal probabilities, and then there is Poisson approximation of binomial also. So these are the few things. So those approximations I have not covered. I will cover those approximations in the next week. The approximations will not be part of the class test sequence.
okay.
So this is what I wanted to say. So there are actually a couple of more things that I want to say. Okay, couple of more interesting problems that I want to solve. So if you can give me a minute, I'll just uh, I'll just open the problem statement, and once I have the problem statement with me, then we can just solve those problems. Okay. So interesting problems related to beta density. Okay. So these densities, you will see why these densities are really very useful and all. So I just wanted to demonstrate the use of these beta densities and all. So you can very nicely relate. So, So can you just give me a minute? I'll get those problems and we'll. So just give me a minute. So there is a interesting document, like handwritten document that is created by Professor Buddhananda Banerjee. So in that document, everything is not necessarily important, but there are few things that are there. So I'll share that handwritten document with all of you today after the class. So once we do that, then we will see how we can do this. Okay. So that document has those interesting problems. Okay, so I'm not able to find that document right now. So okay, here it is. Okay, so I can do that. Okay, so let us look at few examples. Okay, let us see a couple of examples. So these examples are interesting, and these examples we'll see that they are important. Okay, so let x1, x2, xn, let x1, x2 up to xn. Okay, so let x1, x2, xn be IID random variables. Okay, IID random variables with the cumulative distribution function capital Fx. Okay, so they're all IID, so they'll have the same CDF capital. Okay, so that is what we have. And you take y to be equal to maximum of y1, y to be maximum of x1 up to xn, right? So I think you have seen this maximum and minimum example once. One of the examples that we had taken was, I think, minimum of x1, x2 in geometric case. Is that the example that we have discussed in the class?
Yes, sir.
Yeah, so similar to that maximum minimum, I am continuing. So this is something really very interesting. Okay, so what we are really interested in is we are interested in finding out CDF and PDF of one, right? So find PDF and CDF of one. So that is what we are interested in. So how do you do this? So suppose capital GY is CDF of Y. Okay, suppose this is CDF of Y. Then what is this capital GY for any real number Y? So let me do this calculation on the next page. So this GY is basically probability capital Y less than or equal to Y. Then this is nothing but probability of x1 less than or equal to y, and x2 is less than or equal to y, and xn is less than or equal to y. Because the maximum is less than or equal to y, each of the individuals x1, x2, xn is less than or equal to y. This is what it is. And now I'll use the fact that they are independent. So because they're independent, I can write this down as x1 less than or equal to y into x2 less than or equal to y into probability xn less than or equal to y. So this I can say because of independence, right? So this is because of independence, I can say. And then this I can write down as product I from 1 to n f of y, because all of these are f of y, right? So basically what you get is f of y to the power n, right? G of y is basically f of y to the power n, right? And now you take the special case. What is the special case that you take? So the special case that you take is that xi are IID uniform 0, 1. Okay, continuous uniform 0, 1. If that is the case, then what happens? Then what happens? Can you tell me what is GY then? Can you tell me what is GY? Come on, you can tell me what
To the
is.
power n.
Sorry.
Y to the power n.
Y to the power n, correct. So GY is Y to the power n. So what is density of Y? G of Y is nothing but d by dy of capital GY is what? Ny n minus 1, right? And this will happen for y belonging to 0, 1 is equal to 0 otherwise, correct? Can you identify this density? Gy n y n minus 1. Do you know this density? So I'll write this density down once again. So why will it be only between 0 and 1? Because the maximum will always be of x1, x2, xn. They are all going to lie between 0 and 1. So y is also going to be 0 and 1 is equal to 0 otherwise, right? So n y n minus n y to the power n minus 1, right? So this is what you will have gy to be equal to y to the power n, and small gy PDF will be this. So let us write this density down once again. So this is equal to n y to the power n minus 1 for y belonging to 0 and 1 is equal to 0 otherwise. So can you identify this density?
Log normal.
No. So this density is actually beta density. So this density is beta density. This is beta n1. Can you check whether it is really beta n1 or not? What was the beta density that you wrote down? The beta density that you wrote down was here, right? So the beta density that you wrote down is here. 1 upon b alpha beta x to the power alpha minus 1, 1 minus x to the power beta minus 1. You take alpha is equal to n here. So you have x to the power n minus 1, and you take beta is equal to 1. So you have 1 minus x to the power 0. So you have x to the power n minus 1. And what will be this evaluation? According to the formula, beta alpha beta, it will be equal to n. You can just check easily, right? You can just easily check. This is what you will get. Okay, so this is beta n1. So similarly, you can do the calculation for this minimum also. Okay, so this minimum is something that we had seen, right? So that minimum will also give to beta. Okay, so let us write this example down. So what is the example? So same thing again, x1, x2 up to xn, x1, x2 up to xn, they are all independent, identically distributed random variables. Okay, so they are all IID. With CDF capital Fx and PDF small f. Okay. So that is what you have. And now you define the new random variable z to be minimum of x1, x2 up to xn. Correct? You define this random variable x to be minimum of this. And you can say let g of z be the CDF of z. Okay. So what is this CDF of z going to do? Now you tell me. So g of z will be equal to probability capital Z less than or equal to z, which is same as saying probability minimum of x1 up to xn is less than or equal to z. Okay, so minimum of this x1, x2 less than or equal to z is not really going to help, right? So if I write this down as 1 minus probability of this random variable z greater than, is that okay? Is that okay? Do you agree with this statement? And once you agree with this, if the minimum is greater than z, then every random variable has to be greater than z. That's what I can say. So I will say that. So what is this gz? Then this gz is 1 minus probability x1 should be greater than z, x2 should be greater than z. All of them should be greater than z, right? Only then the minimum will be greater than z. So that is what you have. And then I can write this down as probability x1 strictly greater than z into probability x2 strictly greater than z into probability xn strictly greater than z. So this is the calculation that we had done for geometric density, if you remember, right? X1, x2, this was the calculation that we had done for geometric density. And why I can write this down? This I can write down because of independence of x size, right? Because of independence of x size, I can write this thing down. So what is this? 1 minus if you all agree, I can write this down 1 minus fz, right? Because they are all identically distributed, they have this. So this is what you have. So what is this? 1 minus fz to the power n. That is what gz is, right? So again, in particular, you take xi or iid uniform 0, 1. Okay, for I is equal to 1 to up to n. Then what will happen? What is gz? Gz is 1 minus. Now you tell me what will be the gz?
X to the power in
1 minus z, right? To the power
Z.
n. This is what I'll have, and z will be between 0 to 1, right? So that's what I'll have. And when I differentiate, this be the PDF of z. So this gz will be equal to d by dz of capital D gz. And what will this be equal to? Is that right?
Yes, sir.
And this will be equal to 0 otherwise. And you can check again that this is a beta density again, but now this is beta 1n, right? So maximum was beta n1, minimum is beta 1n. So this is something that is really very interesting, right? So note xi follow iid uniform 0, 1 for I is equal to 1 to up to n. Then maximum of xi, right? Maximum of xi. This follows beta with n1 parameters, and minimum of xi. This follows beta with 1n. Right? So this is something that we prove. So this result up to this part is general result, right? So up to this part it is general result. Similarly here also up to this part it is general result. It could have been any density, but I chose x1, x2, xn to be uniform 0, 1. Then you have a special form of PDF, fx is equal to x. That's the form of CDF that I used, and using that form I actually proved this result. So I hope you understand these results. Is that okay? So these are the interesting like reasons why you like have these beta densities. They come naturally if you are starting to look at maximum and minimum of uniform 0, 1 random variables. Okay, so this is something that is really very interesting, because I said something about beta densities. I just wanted to relate those beta densities with something that we have already done. Okay, so I hope this part is clear. Any doubt in this part?
Sir,
Yes.
sir, can you once explain the transformation in the log normal distribution?
Transformation in log normal distribution. So log normal distribution, so you have x is a random variable whose logarithm is normally distributed. Then you will call x to be log normal density. So what do you have? You have this log of x to be normally distributed random variable. Okay, that is what you have.
Yes, sir. I did not understand how we got from how we derived fx of it.
So if y, which is log x, is normal, then what is x? X is e raised to y, right?
Yes, sir.
And then you are trying to find out PDF of x. You know that the log of x is normal, then e raised to y is equal to x. That's what you want to find out. So you have to write it down a little bit. Okay, I have not told you how to derive it. Okay, I will not derive it now. Also, I don't think I have enough time anyway. So for the time being, you can just remember this. Or I think the place where you can see the proof quickly, I think would be the video lectures by Professor Somesh Kumar. There he would have derived it, I am very sure. I have not seen the lectures yet, but he would have derived this log normal density, how you get in Somesh Kumar's lectures. So if you can find from Professor Somesh Kumar's lectures available on NPTEL, YouTube, I think that link was given to you with the syllabus. There you will find the proof of this one. Okay.
Yes, sir.
Yeah. So right now I do not have time, so I'll not go into that. But you can derive with the logic that we have done so far. So the density looks like this, expectation and variance looks like this.
Sir,
Yes.
sir, I was working on a question in which it was asked that the expected number of tosses of a coin to be made till there are either two consecutive heads or two consecutive tails. So, I mean, I was doing it, but I was getting a weird answer. Like I was solving the case when it will end at two consecutive heads, but I was getting number of expected tosses to be less than two. It is not possible, right?
How is that possible?
I was getting that, so I'll have to check it.
Yeah, if you cannot do it, like whatever answer you have, you just write it down and send it to me in this like our chat in this semester. I'll have a look and I'll get back to you.
Okay. Actually, I sent a question to you in that chat too. I mean, it was an assignment question. I was not getting that.
You have sent me already. I'll check it. When did you send?
I mean, that would be the most recent method. That's a different question. That's not this one. This one I'll send after the class.
Okay.
That
okay.
was other question.
Okay. Okay, so this is all I had to say today. So once again, before we log off, exam will be on next Monday. I think that is 4th October. Monday during class hours 11 to 12. The syllabus, schedule, everything. I will just send the PDF similar to one I had shared for class test 1 earlier. So that I will send. The syllabus is like whatever I have done in the class. Basically, these random variables, discrete, continuous, random vectors that I have done, discrete, continuous, up to whatever point I have done. That's what basically the syllabus is, right? So this is what we'll have, and try to solve all the problem sheets that are shared with you. Revise the lecture notes. Even if it is an open book test, make sure that you remember these formula, because you might have seen, like even in this proof I just wrote down this as x to the power n, like quickly took derivative n y to the power n minus 1. So many of you may not remember that gy is of the form y to the power n for this uniform density, right? So it is of the form gy is equal to y. So these are the type of things that quickly are used, or without mentioning they are done sometimes in the class, which you may not understand. So I will say that if you revise all the things that I've done properly, make the chart, even if it is an open book test, it will help. Okay, so I would really request you to do that. And make sure that you are able to see those math symbols correctly in the link shared by me. Okay, if there is any issue, please contact Professor Buddhananda Banerjee. Whatever information he is asking for, that screenshot and everything, please share it and make sure that it is sorted before the exam. Okay, otherwise it will be troublesome in the exam. All the best for the exam, and I'll be available in Microsoft Teams. Yeah, I'll upload the slides also after the class. I'll do that. So please, I note that I'll be available in MS Teams like last time during the exam time. It is not necessary for you to log into Microsoft Teams. You can just log into Moodle and start writing exam on that day. In case you face any problem, I'll be available in Microsoft Teams. I'll start the meeting as usual for our Monday class. I'll be available between 11 to 12 in this meeting next Monday. If you face any issue, you just log into Microsoft Teams and you let me know. Otherwise, it is not necessary to log into Microsoft Teams. You can just log into Moodle and start writing exam. Okay. Thank you very much. All the best and see you next week.
Give me some.
Yes.
Sir, will the syllabus be till taught today, or so
Yes.
will we get
Yes. It will. So I will share the syllabus. So in that document, everything is given. But basically, it is. It will cover like mostly what I have done till today. Okay. So mostly what I have done. But like you cannot say Bayes theorem is not in the syllabus, or like whatever we did in the previous test, those concepts anyway will be required, right? So that I cannot really say you. So But whatever I have covered so far, you can consider that is okay. But exact topic names and everything is mentioned in the document I'm going to show. Is that okay, Shashwat?
Yes, sir.
Yeah. Okay. Okay. Thank you. See you next week.